Thank you for the organizers of the conference. Happy to be here. So my talk will be about some recent developments of the algebraic geometry inside Matroid theory. And so this talk will be very elementary. I won't even define what a matroid is. And if there's time, I will say something about some joint work with Alex Fink, Raj Gandhi, Liu Jiang, and Connor Simpson. So that's it. So I'll start with a fixing a basis on C to the E, where E is the set 0 up to n. Comes with the standard basis indexed by elements inside E. And then I want to pick a linear space. It also has a dual basis. I'm also going to pick a linear space L sitting inside E. And then the co-basis of this vector space gives me a close embedding of PL into P of N. And then I'm going to say, what is P? So it's the projectilization of L. So this is a vector space. You poke out the origin. There's a C star action on L. You action. So and it maps into Pn. So concretely, a vector V, the equivalence class of vector V, maps into F0 of V all the way to Fn of V. Okay, so these are co-bases. So and then a matroid. So definition. You just said a hyperplane arrangement. A hyperplane arrangement is PL together with like pullbacks of coordinate hyperplanes inside Pn. So I have HI defined by PL intersects with the locus where Fi manages. So these are my coordinate hyperplanes. So this is my definition of matrix. And then I'll give examples later, but let me say I'll give more definition. So a flat of a hyperplane arrangement is a coordinate subspace. So it's given by some intersection of HIs. So it's some coordinate subspace. So you notice the coordinate subspace inside PL, they form a process ordered by inclusion. So this is why this is and then this process has a well-defined joins and meets. So you can intersect process, and you can also take like the some. You can also take you can also add to linear space, expand. So addition of two linear space is well defined. So this is the joins and meets of inside the process. So this and then the So L is going to be the posets of flats.
So defining a hyperplanar arrangement is equivalent to just choosing some linear subspace of Cn plus 1. That's all you need.
Yeah. So and then you also need a basis for the ambient space. So that you, and then you're looking, and then your hyperplane arrangement is going to. So there's a there's an algebraic torus inside this. So you take the intersection of the of this guy with PL that will pick out the unions of all those the bounds and boundaries of PLs. Those boundaries would be your hyperplanes. So this is the same data. So any other questions?
So you're fixing it out the flats form a poset, or what
the flats form a poset. Yeah.
Yeah. Okay. So, and you're considering the points. Yeah. A flat of what is that? A is some what?
It's some intersection of HIs. So like some coordinate subspaces. So let me maybe non-empty intersection. Okay. And then some examples. So let's say I have a graph G, and with vertex with vertices E, and then I'm going to take my my hyperplane to be. So I can just like I won't define the I don't need to define what the ambient space is. I can just define what the hyperplane is that would pin down this posets. Okay, so I'm going to define my hyperplane to be Fj. So I'm going to put this hyperplane is inside A. If and only if Ij is an energy.
So what are you defining this way? What are you defining? Are you defining A this way, or are you defining?
I'm defining A this way. Yeah.
But A is PL together with some hyperplane. Coordinate hyperplanes.
Yeah.
So we need to define some projective space and some divisors.
I'm going to take the so PL in this case was just going to be the this is sorry by this vertex E I mean I should say that I'm having C, I'm just embedding Cn to Cn. And then like this is like a funny way to do this embedding. Sorry, I'm embedding Cm to some bigger Cn, but in this case I'm using Cn as my. Okay, let me give an example. So let me pick 4 general hyperplanes. Oh, maybe I shouldn't use E. That's where the confusion.
That's not. Those are different E's, right? No. What does the graph have to do? What is the graph in this?
I'm using graph to decide which hyperplanes to put in.
Okay.
So dualizing, dualizing, taking a hyperplane is the same as taking points in the dual. So you can think of, you have 4 general vectors, So this is like 4 general hyperplanes, and this corresponds to this graph.
Is this the map union thing? Or
Yeah,
Yeah.
it is. Map.
You have like pizza here or
Will eventually be like,
what bar?
and enjoy the very exciting.
Okay, so the graph is what you started.
Oh, just sit down.
I start with this graph, so I have 1, 2, 3.
You give me
I have
coffee,
one,
just
two,
walking
three.
in and more like shouting, "Where's the pizza?"
I'm
Is it down?
0. And then I have I have 4 hyperplanes beating this way. And then we define the hyperplane arrangement inside PL when my PL is just going to be P of E. I'm not so this E is not the same E. Okay, so this E here corresponds to this E choose 2.
What about L there?
L is PL is PN here. So this is embedding P4.
A is the number of.
Yeah. So this is embedding P4 inside P6. So because 4 choose 2 is 6. P5. So P5. P3 into P5.
I still don't understand it. So you had a graph, then you define something else. From that graph, you define something.
You define a hyperplanes. You define some hyperplane arrangement according to the static graph.
Yeah.
Yeah.
So I think you had a graph, then you drew some.
This is the hyperplane I put in. Whenever E is an edge, whenever ij is an edge, I put in this hyperplane
Hyperplane where?
inside Pn. So P prime.
Are you embedding the graph into your projective space?
I'm not embedding my graph. I'm embedding a linear space inside a different linear space. I take the intersection with the coordinate subspaces that will pick out the hyperplanes.
Essentially, you're just like taking a graph, getting a corresponding set of hyperplanes, and it intersects based off the condition of like whether the vertex.
Yeah.
Okay.
So there's an implicit statement that there exists an embedding of this smaller projective space into a larger projective space, such that all of these hyperplanes are coordinate hyperplanes.
Yeah. So this will embed. Yeah. So let me give you another example. The 1.2. So I can take. Let me take the complete graph on all vertices. Okay. And then this will give me the array arrangements. So you can count there are 6 hyperplanes here. This will give me the array arrangement. Okay.
So what exactly is this diagram represent?
This is the graph.
This is inside of P4.
This is the arrangement.
I just got.
Yeah, it's this. Okay, so the linear space is E prime. It is still E4.
P4.
Huh?
P3.
P3. Because this will drop dimension by 1. But
This picture is in P3.
yeah, and then I'm still embedding into P. I have more edges, so I need to embed into. I need to embed into higher dimensional space. Okay. Okay. So let me define the Moebius function on the lattice is going to be so it maps. It takes in two elements and gives you some integer. It takes so by some recursive way, x y is going to be 0 if x is not compatible with y, and then if you compare with itself, you get 1. And then if x is strictly less than y, then u of xy is going to be minus x and y. So you have this relation. So the sum. So this is some balancing condition on your Moebius function. So if you do analysis in number theory, you may see this definition somewhere. You may see the word Moebius function is used in some in some setting, but this is the one they used to do in algebraic combinatorics. And then I would define the characteristic polynomial of arrangement is going to be I of t is going to be the sum over f. F as a so PW is going to be some coordinate subspace inside my L. L is the lattice, and then I will put mu of minimum. So because I have a poset, I can define lattice. I can define what the minimum is. PW. And then I have T of
If you want this to be lattice, you need to drop this assumption that the plot needs to be non-empty. Strictly speaking, there needs to be a minimal.
So this is what a characteristic function is. This looks like very mysterious, but I claim that you have already seen this in a lot of settings. In the case of graphs, this is the what?
Sorry, what is
A lattice is a poset with a join and meet. So you know what poset is?
Yeah.
You can do a join. There's a unique. If you have two elements, there's a unique element that dominates the two, and the meet is okay.
Wait, sorry, you're taking the minimum of the whole lattice.
The whole lattice.
Isn't that just always the empty set?
No. You can have all the hyperplanes that meets like the intersection of every single hyperplane doesn't have to be like trivial. For example, you can have like two planes that meet in a line. You call that a hyperplane arrangement. Then and the central arrangement is still the minimum is still that line.
Wait,
projectilization line.
so L positive flat doesn't mean it's the poset of all flats.
Is the poset of all flats.
All coordinates hyperspace hyperplanes do intersect just at 0, right?
Yes.
So the intersection should be
No. I mean, what if for example, my PL, I can live totally inside a single coordinate hyperplane.
yes. Well, Yes, but then the
Wait,
intersection with the other coordinate hyperplanes will still give you.
That's why I said non-empty.
So L is just the poset of all non-empty flats,
Yeah,
but then it's not a lattice.
it is a lattice because what do you mean it's not a lattice?
And what if two hyperplanes intersect just a, or what if some set of hyperplanes intersects an empty set? Then their intersection is not a flat anymore.
It's not flat, yeah.
So the meter is not defined.
It's defined to be the empty set.
But L is a poset of non-empty flats. So it's not.
Sure, I can put to get so maybe I said together with this and then L.
But then the minimum element of L is just the empty set. Yes, that's what the original question.
Let me think. Um, uh, fine. Sorry.
And if it's so, it's not always the empty.
No. If you have two coordinate hyperplane, if it's like completely contained in a single hyperplane work. Maybe I don't understand the question.
Yeah, okay. If it's not always the empty set, we can discuss it after.
It doesn't have to be empty set. So example here you get you always for graphs you always get the characteristic polynomial of your graph. What's the question?
Can I get a more concrete description of PW?
PW is a projectization
Of a sub
it's a coordinate subspace. It's the intersection. So in this case, the characteristic polynomial is always the chromatic polynomial of a graph. So in this case, it's going to be 1 minus so when you plug in k, you get the number of k colorings. In this case, it's going to be so this is the complete graph. So so you can prove that for the mu of A and B. So if you have when you have elements A inside B, inside N, inside E, and then mu of A, mu of B, A and B is just going to be -1 to the B A plus that. This is always going to be your characteristic function, and then so what that tells you is that the characteristic polynomial is going to be t minus t minus 1 to the n.
That's specifically for the graph.
It's true. It's only true for the object graph. So And then there's a conjecture by Rota, Hebron, and Welch. And there's a theorem by Juni, and others. That the coefficients of the reduced, so this is called a reduced characteristic polynomial, because by the definition of the Moebius function, when you plug in one, you always get 0. So like doesn't hurt to make this reduction. Has it's not concave in absolute values. So concretely, so the reduced characteristic polynomial always has alternating coefficient, which is not too hard to show. So let's say if I write say so let's say if I write the coefficient like this, and then being log concave means the Li squared. So mu I squared is going to be greater or equal to mu I minus 1 and mu I plus 1 for I.
The absolute value.
Yeah, so this is, so I'm killing the absolute value here. Is you always have alternating coefficients. Yeah. So for example, you see in the case of chromatic polynomial, so this is like minus plus minus. It's very easy. Okay, so I will proof outline, and I will sketch the proof outline. In the case when your matrix is realizable. So in the case, so your matrix being realizable means it's the hyperplane arrangement. So I'll prove it in this case. Okay. So so the strategy is to I guess what Jim must be doing is that he was trying to count points on so he was working over finite views, and he was counting points. So this is what the so this is actually what the chromatic characteristic polynomial is going to do for you. Some special cases, but over finite views, where you're not working with C, and then there is some log concave kind of. So the only source of log concavity in the world in algebraic geometry is mostly the Kovatsky-Tessier inequality. Okay. What this is saying that so let X be a compact Kähler manifold if projected variety over C, if you like, and then let alpha and beta be two net currents for nav divisor, nav11 class. Actually, so be two. It's like two. You have two nav divisor on a plane. So if you don't know what nav is, you should think that. So I can have a curve inside my compact Kata, and then I'll Riemann surface if you like, and then restrict my one form to restrict my one form to the curve. That will give you something, and then integrate. The result of this integration is always going to be negative. So this is what it means to be nav. So, and then I would let gamma to be a prime class. To be so let's say so this is going to be in a numerical class in actually I can just take child. V of x. Oh, there's no child. Maybe. And then this is the class of a actual multiple of an actual submanifold. So submanifolds. So it means it has to be reduced and geometrically reduced and geometrically reducible. So then the sequence when you integrate R minus 9. So this guy is going to be locking K. Okay. So this is the statement. So the proof is actually not very hard. You just need to well, the proof in algebraic setting is not hard. So what you do is that you take the so you can always like do induction or dimension. So what you do is that you reduce to the case when when d is 0 and this is just the entire of x, so a multiple of the entire of x. This needs to be effective. So this is thank you. And this and then you can always do this by Bertini, because you can, and then you reduce the number of divisors. You also do apply Bertini to these guys. Before this, you need to, before applying Bertini, because this is because the being locking cave is like a less than or equal condition. So you can approximate your class by ample divisors. So you approximate these guys by ample divisors. So you can also assume these guys are ample. Okay, so assume alpha, beta are ample. Okay, two divisors on the surface X. Okay, and then what you need to prove is that integral alpha square, so you reduce the problem to this. But this is just Minkowski of the Newton concave body of alpha and beta. So you're done.
Okay. Should that be 2n lines? Instead of just
Should be,
no, not that one, but the
okay, okay, so now we want to interpret the coefficient here as some numbers you get from these, some numbers like this. So step two is so let's say I want to blow up Pn by all of these coordinate subspaces. So ideally, if all my hyperplanes are actually, all these flats are actually, well, it'd be nice if they are all divisors, then I'd be very happy. So what I'm going to do is that I'm going to blow up Pn by, there's a sequence of blow up x1 all the way to x of n minus 2, and this I would call x of an. This type an dimensional combinatorics. What this is how do you get this? Okay, so xd is going to be the blow up of the strict transforms of d-dimensional subspaces, coordinate subspaces, inside x of d minus 1. Okay, so you have a sequence, a massive sequence of blow up that that gives you this thing, and then exercise show this blow up resolve the indeterminacy locus of the chroma transform. So it sends x0 all the way to the xn to this is the inverse every single coordinate of your points, and this is not defined everywhere. It's defined inside this inside the algebraic torus inside your projected space, but it's not defined everywhere. Okay, and then so I have the linear space inside this PL. What I can do is that I can take a strict transform of this linear space inside the Combinatorics variety.
what's L? Sorry.
L is a linear space. Yeah, you can. Yes, I can take a space. Ideally, I would want my linear space to intersect the open torus. So big open. So
And why are you taking an arbitrary linear space? I don't think I'm following.
because this is the defining data of a matrix. You just need to fix a linear space. Sorry, of a hyperplane arrangement. So
You're proving.
this is a hyperplane arrangement A.
So is the L for coming from the hyperplane arrangement of A the same as the L over there, or are they?
Yeah, it's the same.
All right.
You have PL. You take the strict transform. This I will call WL. Okay. This will be This has, and then I claim so WL, so WL is the De Corsini-Processi wonderful model of compactification of a linear space. The important information is that this class is Poincare due to some current I would call delta of L inside inside my variety. So what is current? What is this current? So because I'm working with a toric variety, my subvariety is freely generated by torus invariance. It's like by the torus invariant subvarieties. Because I can always deform my any cycle into a union bunch of torus invariant cycle. So by taking a toric degeneration. Here, so in order to define what a current is, or an algebraic cycle is, I just need to know how does it act on a torus invariant subvariety. The torus invariant subvariety inside this particular toric variety is indexed by chains of flats, so chains of subsets inside this ground set E. So I'm going to write rho E as the convex rho, so maybe F as the cone of chain F1 up way to FD of my inside E. So this is a chain of flag of subsets inside E. So this will index and this will index a subvariety, the T invariant subvariety. T is a torus. Yeah. So T is going to be C E G M E. Yeah. So this is the T invariant subvariety inside, which we're gonna V of rho F inside H inside. Now I'm using Chow. It doesn't matter actually because you have a smooth projective variety over C. So I'm using Chow of D of X. Okay. Okay. So now I'm going to tell you what this current or.
Sorry, how does the flag define your subvariety?
It defines a cone, and then so a cone would define if a cone. This is a honest cone inside the co-character lattice of your torus, and then you take the co-character. You take some torus orbit closure inside the co-character lattice.
Wait, F is torus invariant.
This is torus invariant.
Every single Fi is not in torus.
No, Fi's are. So these are actually just. No, I'm not saying the. This is any subset inside it.
How do you define a
It's a subset, it's not necessarily a coordinate subspace.
but how do they define the cone then? How do they define a cone?
I won't tell you that. You don't need to know. So this current is gonna sense this cycle to 1 if so it's going to send things to 1 if so if f is a maximal, so f indexes a maximal flag of flats and 0 otherwise. So you have a maximal chain inside a poset. So F is some subsets inside the n-element set. So every F you take in defines the bunch of hyperplanes you are taking the union of. So these F will define, so every single Fi gonna pin down a coordinate hyperplane. And then if F is a maximal sequence of coordinate hyperplanes, it's the longest flag you can have inside your inside L, and then this will be 1, otherwise it's going to be 0. And then the upshot is that mu, and then upshot is that mu k, mu k, yes, it's going to be the number of such guys.
Sorry. So if even one of Fi is not a coordinate subspace, you get 0.
Okay, say that again.
So if in this flag even one subspace is not coordinate, you just get 0.
They have to be coordinate subspaces.
But what if you started with a flag of coordinates subspaces, but
so-
then formed it?
So F is an element. Fi's are element inside E, so you can only use it to define coordinate subspace. What you need to be worried about is the dimension doesn't jump, or it jumps too much.
Because I'm pretty sure.
So number of maximal flags in L, but this is just going to be the degree. This is going to be alpha I and then beta of r minus I, where r is the dimension of L of PL, right? Minus I, and then you take the class of, and then you do this. Okay, and then you integrate over x. Okay, yeah. And so this proves the log concavity. So I think the non-obvious part is this. So I can say briefly what this string alpha and beta does. So alpha is going to be, so you see there's a blow up here, alpha, and then we'll call this map pi 1. Alpha is going to be pi 1 inside pi 1 of O1 of O1, so it's PN. Okay. And then beta is going to be pi, and it's going to be the chroma pullback of I1 and of O1. What's that? The chroma is the exercise. So this resolve the indeterminacy locus. So like you can so that this makes sense. So like the chroma transform is an actual involution on this variety. So this is what you can. So this is quantified. So what this is doing is that alpha, being a general hyperplane, is like truncating your lattice from the top. So you throw away all the top, all the big like the top, so you have this graded lattice. You're throwing away all the flats in the very top, and this will define you a new lattice. So what geometrically you should think that you have PL and then you have a general hyperplane like that intersects your PL that cuts down the dimension by 1 and kills the codimension 1 flats. They replace all the codimension 2 flags with the codimension 1 flags.
Alpha to the I intersects you with I general hyperplane.
Yeah.
What does beta?
Beta. So what beta does is that you're truncating from below. So it's not obvious. So
What kind of sections does this sheet have? But it's not hyperplanes, but it's some
this one?
Yeah. geometric.
So the chroma transform is coming from a singular linear system. So this is a linear system with base point. The linear system is given by multiplicity and hypersurface at degree n+1 hypersurface, degree n-1 hypersurfaces inside the projected space. And then the reason why this is given by truncating from below, the only proof I know is not very geometric. Sorry. So, you can sort of visualize what the image of a hyperplane is the chroma transform in some low dimension. So for example, if you have P1 Veronese into P3, the chroma transform is going to be the rational. The chroma transform is going to be the rational, just going to be a straight line inside P3. Conversely, if you have a straight line inside P3, if you take the chroma transform, you get a Veronese. So, yeah. So you have two base point free divisors. So they're obviously NAF. So this is locking head. And this proves that conjecture in the case of hyperplane arrangement. This is true, and later what Jun and Eric Katz and Karen Presido did is that they prove it for non-realizable matrix. So non-realizable matrix is you don't have a linear space, but you still have a graded geometric lattice. This lattice is graded, so it has a well-defined, well, it has a grading on it. It's generated in degree 1, rank 1. So this is generated in degree 1. This is because you can build every single element in your poset by taking joints of degree 1 things. And then Kowalski-Tessier this doesn't go through. So because Kowalski-Tessier requires you to have you used to know that you're working with a prime class. So a prime class means is a positive Q multiple of a class of an actual subvariety. It is still true that you can define delta for any matrix, but the problem is you cannot show it satisfies locking this kind of lock concavity property.
Because it's not a prime.
Yeah. So so an example of something that is not realizable is that you take. So now I'm doing. Say. I'm taking dual of the hyperplane arrangement that gives me points arrangement inside the dual picture. So let's take the Pappas matrix. Oh shit. This should intersect and so good. Okay, so the picture is a bit hard to draw, but let me tell you what. So if you Google Pappas, so Google Pappas, a hexagon. You see some picture. You remove the middle line to get the so. Let me try to draw it again. And then you do this. And then this. But I don't put in this line. So there's a line here that I don't put in. So these are my hyperplanes, but I don't put in this line. Okay, this still defines the geometric lattice, but it doesn't come from a hyperplane arrangement. If it does come from a hyperplane arrangement, there's going to be a hyperplane that goes through these 3 points, just by instance, just by like high school geometry. But like I'm not putting in this point, I'm just removing this point. So it's not a hyperplane arrangement. So and then okay, so what do you do if your thing is non-realizable? So what you can do is that you have PL, you have the blowout PL.
If you remove this line, then this is no longer a lattice, because
It is a lattice.
this line is the meet of 2 of the points, and it doesn't exist anymore.
Meet what?
This line is a meet of 2 hyperplanes.
What hyperplane? Every hyperplane goes.
Points are hyperplanes. This line is the line passing through 2 points, so it is supposed to be
3 points.
Degree 1 is representing some element of.
At least 2. Okay. So yeah. So what I do is that I just take so the the joint is going to be right. You say the joint is problematic or beat is that?
well in this dual picture. It is the joint. In the original picture, you can see a line of the 2 hyperplanes. You just removed it. You removed it.
Shouldn't line on you.
Yeah.
So why is it still a lattice?
What's because you have I mean you can because the meat
How about you wait until the talk's over? Then you
meat is going to be empty.
Yeah, wait until the talk's over.
There's no hyperplane.
You saying something?
Their meat is now something else.
Oh, it's fine.
Okay, so the joint is going to be the entire plane, the entire set, the entire ground set. The meat is going to be empty in this situation.
Oh, but that's very degrading.
The empty set is on degree 0.
Yeah, so somehow we intersected 2 things of dimension n-1 and got something of dimension -1.
No. The points are as the points have. I didn't tell you what is the grading of the degree of the point. In this case, a point has degree. I'm grading by code in the hyperplane picture. I'm grading by code dimension. So what do you do in the realizable case? Sorry, in the non-realizable case. So you can have combinatorial description for every single one of these strict transforms. I'm not writing down all the strict transform, but you still have the combinatorial model for the child ring of every single one of these strict transforms. What you can do is that you can prove that these child rings, they all satisfy a Kähler package. So the Kähler package includes the Poincare duality, Lipschitz, and Riemann. And then these two, when you restrict to that virtual class, restrict to that child ring, still satisfy the Lipschitz property. So they still have the half Lipschitz property. So you get a locking cavity using Hodge index. But the hard part is actually to show that like this combinatorial child ring has the or the Kähler package that you need. Yeah. So I guess I don't have time to talk about these. Thanks everyone. I think I'll end here. Any questions?
So you end up proving locking cavity without using the Hovansky type.
We did.
I mean, in the non-realizable cases.
In the non-realizable case, you don't. But Hovansky-Tasia, the actual well, this is actually just just a special case of the Hodge index inequality. Like this is Hodge index. This is like how. So I think I raised the proof for the surface case. The surface case, it is the same as Hodge index inequality for a surface. And then the general Hodge, the general version of Hodge index. There's many different generalization of like Hodge index type inequalities. Like you can take like more than two devices. You can take like n of them, and then you compute some, and then you compute the mixed volumes. So like you take the so for example, you can do the product of like hi, and then product of like, and then you multiply by the product of like di. So these are all F classes. So x. So you have like dimension many of them, okay? And then okay, let me give you a version that is like easy to state. So let's say I have h0. Sorry, so I have alpha, and then I have a bunch of depth classes, beta, a bunch of depth classes, and minus one of them, and then I can put alpha, beta, and then this is less than alpha, beta of oh.
Wait, what is this supposed to be? What is this supposed to prove? Like, what is this?
What is what?
What is this?
Oh, I'm just giving you a general version of like various types of Hodge index inequality. So there are many different types of like Hodge index inequality that you can deduce just using like the Hodge-Riemann relation.
They call index inequalities, I guess they're related to using an index.
Because well, they are related to computing index in the surface case. In general, I think so, but I'm not sure. Yeah, I'm not sure about the general case, but in the surface case, you are just computing one countries.
Alright,
Okay, you can go ask question, go ask question. You said, in the non-realizable case, we can define this class delta L,
Yeah,
even though we don't actually have the sub, variety
Yeah.
WL. But, so,
So
is having delta L equivalent to having a major project?
it, so what delta is, delta L is called a, it's, well, so, well, no occurrence on on this toric variety arises this way.
Satisfying some condition.
Well, it satisfies some conditions, so, so what it actually is that like, intersection theory on a toric variety is actually the same as intersection theory of tropical variety inside tropical very affine variety, tropicalization of very affine varieties. What's actually true is that these delta L's are something called a tropical linear space. So tropical is true. Not all tropical linear space are tropicalization of actual linear space. Okay, but it's true that like there's a one-to-one correspondence between tropical linear space and matroids.
By tropical, you mean tropical semi-ring? So
Yeah, so what you do is that you take
the one thing I actually understood of
the tropicalization means that you're taking a weight degeneration of your variety, of a very affine variety,
right.
and then you take the weights the collective weights such that the weight degeneration beats non-trivially with the big open torus inside PN. So this is what tropicalization means.
All right.
Thank you.
So feel free to grab some pizza.
The election now open, so you can like nominate if you want to like run.
Not pizza.
What's the question?